Section 6.6, solving logarithmic and exponential equations. So some properties of logs: if we have log base a of m is equal to log base a of n, then it has to be that m is equal to n. So if we have the log of the same bases, what's inside them has to be equivalent. M and n and a are positive, and a cannot equal 1. And this follows because logarithms must be one-to-one functions. So a little bit of practice with this. Here we have 3 log base 4 of x is equal to log base 4 of 125. Well, if we go back to that property right from the previous side, we have to have just the logarithm. So to have just the logarithm, this number out front can become the exponent of 3 based off of this property right down there, the power property. So we have log base 4 of x to the third is going to equal log base 4 of 125. If that's the case, everything is the same, so this x to the third there is going to have to equal 125 from this property right before. So cube root that, and we're going to get x is equal to 5 times 5 times 5 is 125, so x is equal to 5. Just double check that this doesn't cause any issues with domain. For the domain of logs, x has to be greater than 0. That would satisfy it. There would be our answer right there. This one here looks a little bit different, but trying to solve it, we have 2 different logs. Generally a good principle is to try to write this as one log. So we have the difference of 2 logs. This property right here, we can write it as one log with a quotient. So you're going to have log base 3 of the first is going to be on top, the x plus 4 is going to be on top, over the 9 is going to be on the bottom, is equal to 2. Once I get here, I only have one log on one side. So we're not going to use quite the same strategy as before. This time, change it into exponential. It's going to be 3 to the second is equal to x plus 4 over 9. And that just follows from the definition of a logarithm. This is 9 is equal to x plus 4 over 9. Multiply both sides by 9. We're going to get 81 is equal to x plus 4. Subtract 4, subtract 4. This is going to be 77 is equal to x. Just double check that that's not going to cause any issues. If we put 77 in here, this is still going to be a positive up there, so that should work out just fine. 77 is our answer. This one here, I see lots of logarithms. If we try to condense it, so we narrow this down a little bit, on the left hand side we have a plus in between 2 of them with the same base. We can use this property right here, the sum of logs. So we're going to write this as a single logarithm, log base a of the product of the 2. So x times x minus 2, and that's going to equal log base a of x plus 4. Well, if these 2 logs are equivalent, they have the same base, what's inside the x times the x minus 2 has to be equal to the x plus 4. So once we have a single log on both sides, we can set just the insides, the x times the x minus 2 equals the x plus 4, set those equal to each other. To solve this, we'll get rid of the parentheses, x squared minus 2x is equal to x plus 4, and then subtract x, subtract 4 from both sides. So we're going to get x squared minus 3x minus 4 is equal to 0. Maybe I can factor this, x minus 4 plus 1. If I set the x minus 4 equal to 0, I'll get x is equal to 4. If I set the x plus 1 equal to 0, I'd get x equals negative 1. Let's take a look at these 2 answers. Are either of these going to cause issues? So the 4, if we take the 4 and put it in for the x, it's still positive, still okay. If we put the 4 in for the x here, 4 minus 2 is still positive, it's okay. Put the 4 in here, 4 plus 4 is positive, 4 checks out. 4 is okay. -1. I put -1 in here. We'd have the log of a negative. The domain of logs, these x's have to be positive. This would make it not positive, so I cross that off. And I only have one answer of 4. Solving some exponential equations. If a to the u is equal to a to the v, then the exponents have to be equivalent, is what this is saying. So then u has to equal v for a greater than 0 and a not equal to 1. So if we look at this equation, 3 to the x plus 5 is equal to 27. If we can somehow write the 27 as a base 3 to some power, then we would have two bases that are the same, so only their exponents would have to be the same. Well, 3 to the third is 27, so for these to be same, the exponents have to be the same. The x plus 5 has to be equal to 3, so x is going to have to be -2. And we end up with the answer of -2. How about this one? Here, the bases are not the same, but there's exponents that have variables. Bases aren't the same, exponents that have variables. We're not going to be able to just set the exponents equal to each other because the base are not the same. So we have to somehow get the variables out of the exponents. In order to do that, what we're going to do, we're going to take the log of both sides. So we'll take the log of 2 to the x plus 1 is equal to log of 5 to the 1 minus 2x. And notice I used just log. I used just log because I used a common logarithm, which is base 10. So even though I'm not writing a little 10 there, you can assume it's there. For these two logs, what's nice about logarithms, there's the property that this exponent can come down in front. So when that exponent comes down in front, the x plus 1 times log of 2 is going to equal the 1 minus 2x times log of 5. Well, how does this help us? Now we can distribute the log into both of them. So we're going to have x log of 2 plus 1 times log of 2 is just log of 2 is equal to 1 times log of 5 is just log of 5 minus 2x log of 5. This might look messy, but now we have x's that are in a single term. So I'm going to add 2x log of 5 to both sides. And so on the left hand side now I'll have x log of 2 plus 2x log of 5 plus log of 2 is equal to log of 5. I want to get my variables by themselves, so I'm going to get this other term that doesn't have a variable onto the left side. I'll subtract log of 2. And so now we have x log of 2 plus 2x log of 5 is equal to log of 5 minus log of 2, like that. Here I can factor out the x's. So you have x times log 2 plus 2 log 5 is equal to log 5 minus log 2. If I divide by this on both sides, divide by the log base 2 plus 2 log of 5, log of 2 plus 2 log of 5. You're going to have x is equal to, well, this whole mess here, can I clean this up? Make it look a little bit better? Sure. So we have log of 5 minus log of 2. They have the same bases, so I can make that 1 log of the first over the second. So we have log of 5 halves all over log of 2 plus 2 log of 5. So again, log, if I write this as a single logarithm, it'd be 2 times this 2 would go to the exponent of 5, so 5 to the second. Well, this is just x is equal to log of 5 halves over log 2 times 5 squared is going to be 50. Like that. Now it says express irrational solutions in exact form. This right here is exact form. That's what this is. So we simplified it and got it into exact form. Now the irrational solution, if you were to do this and actually type it in onto your calculator, so type in log of 5/2 divided by log of 50, the number you're going to get is 0.234. If you had to give the decimal approximation, you will on a few assignments in your homework, you have to use your calculator to do that. I don't know a different way to get to it, but if you have to do a decimal approximation, that type of a question wouldn't be on the test. So this is approximately this here, and if I wanted to check this answer, I would take this, I would keep the full number that's on my calculator, so I would do 2 to that answer that's on my calculator plus 1, see what that is equal to. So I do 2 to the power of that answer plus 1, and it comes out to be 2.353. Now I check the other side, 5 to the 1 minus the 2 times that answer that was on my calculator. So 5 to the power of 1 minus 2 times, and it comes out to be 2.353 again. So it checks out. This is the correct answer. Good luck. Again, if you're looking for something that's a little bit more in depth, you can always go to the author in action videos, which are in the chapter contents on the left hand side of your My Math Lab screen.